Okay, welcome back. Today let's finish up our discussion of the geometry of the plane. We're emphasizing those aspects of the geometry of the plane that are going to generalize to curved spaces. And we left off at a short discussion of the parallel postulate in general geometries. Well, we all know the parallel postulate in Euclidean geometry. Given a straight line L1, a geodesic of arbitrary extent. If we have a point P outside of that line, then the postulate says that there's a unique line called L2 here, which never intersects L1. That line is called parallel to L1. Okay, and of course we're used to that and very comfortable with that. The point is, however, that in spaces with curvature, it's not true. Okay, for example, if on a sphere or if we have hyperbolic spaces, we'll see that the parallel postulate is not true. In fact, it was the discovery of hyperbolic geometry which led to some of the big developments in mathematics in the 19th century. The demonstration by Boyer and others that there was a hyperbolic geometry, a geometry in which the parallel postulate was not true, in which, as we'll discuss when we work out the Poincare disk model, there are many alternatives to parallelism there. Okay. The last thing we want to turn to is to think about the rates at which geodesics diverge if they begin at a single point in a flat space. It's a very simple consideration, but we'll find out that the generalization of this idea to curved spaces tells us a great deal about the geometry and in fact the intrinsic curvature of those spaces. This is a critical idea in general relativity. Okay, the rate at which geodesics come together or deviate becomes a measure of the Riemannian curvature of those spaces. Okay, and we'll want to understand that. We'll be here studying it just in the context of classical differential geometry, and we'll want to develop differential equations to describe the rate at which geodesics deviate from one another as we move along in the space. So here's the situation in R2. In R2, we have two lines, those straight lines. Those are geodesics. That idea generalizes to other spaces. They're emanating from a point P, as shown here. And initially, they have an angle phi. So I choose a direction here and a direction here with an angle phi between them, and then I look and calculate the rate at which they deviate from one another. Since they're geodesics, I call this the geodesic deviation. Okay, and that's shown here in the picture. Well, it's clear that it's a linear problem here, and so the further out I go, the greater the distance between them, and the relationship is linear. No, I don't need to make a big to-do about that. Okay, and that's the situation. Now, when I come to spaces where there's positive curvature, we'll find, in fact, and we'll demonstrate this in the case of the sphere in an upcoming lecture. Okay, that if k is greater than 1, the rate of growth actually is less than linear. Okay, and in a space with k negative, a hyperbolic space, the rate of growth is more. They deviate more. Okay. The geodesic deviation gives us a natural measure of curvature. Okay, we'll write down a differential equation for the deviation, and see that it's controlled by the Gaussian curvature. All of this is very important in general relativity, okay, because in general relativity, tidal forces measure the curvature of space-time locally. Okay, so in general relativity, we imagine problems like a spaceman outside of a black hole, outside of the horizon of the black hole, hopefully, dropping a couple of balls. Okay, when he drops the balls are then they're their rest frames are then inertial, locally inertial reference frames, but there are no forces in the accelerating frame, as we've discussed, and we'll discuss more when we turn to general relativity. But those are inertial reference frames. Okay, at least locally they're inertial. Well, the point is that any non-uniformity in the gravitational field, okay, is going to work on those 2 points differently, and they might experience a relative, quote, attraction or relative repulsion. It's not a force between them, it's the fact that they're moving through a curved space. They'll travel on their geodesics, and their geodesics might come together. Well, certainly here on Earth, if I drop 2 balls here, they'll come together because they're both attracted to the center of the Earth. I can think about that problem from Newtonian point of view of forces in an overall Euclidean space. But more importantly, I can think about it from the point of view of general relativity, okay, where space-time is curved and the balls follow geodesics. Okay, they're tiny balls. There's no force between them, but they're in a large, warped space-time. Okay, they feel the effects, in Newtonian words, they feel the effects of the force of gravity due to the Earth, and of course they come together. Okay, and that coming together is a geodesic deviation, and the rate at which they come together is a measure, okay, of the local gravitational field or the local curvature. Okay, when we come to general relativity, we'll develop the equation for the geodesic deviation and see that it measures the components of the Riemann curvature tensor. And here in classical differential geometry, we'll do similar exercises. We'll look at geodesics and see that the distance between them is a measure of the Gaussian curvature. So that's where we're headed. We want to start with this linear, simple situation in Euclidean 2 space, and then we'll develop the ideas from there. Okay, so it's a short lecture today. Now, the next lecture, we're going to turn to spherical geometry, and I'll see you then.